the channel Physics by IITians. Today, we are delighted to have a special guest in our channel. We heartily welcome Mr. Suryan Asthana. He is currently pursuing his doctoral research on the topic interrelation of non-classicality features and application to quantum communications. Let me give a short introduction about him. He did his BSc in Physics Honours from Kanpur University. He was a gold medalist in physics, MSc in physics from IIT Delhi. During his PhD, he has published 10 highly reputed journals and 5 international conference papers. He also wrote single author paper during his PhD independently in the field of quantum communication. So welcome, sir. Welcome to the channel.
Yeah, thank you, Sati, for having me here. We will discuss as we go along the interview questions of quantum information and quantum mechanics in general.
Yes, sir. Actually, a lot of the students ask me what are the topics to learn for pursuing research in quantum information theory or theoretical physics, and the possible questions that you have already faced during interviews that you can help the students that how they should prepare for it. So please, over to you, sir.
So the point is that as we all know that when we go before an interview panel, mostly we are asked one particular question: what is your area of interest and what are the areas in which you want to work? So let us say we give an answer quantum information. So then it is expected from us. So any answer that we will give, let us say we will say some Fourier optics or some imaging. So we should not, number one point is that we should not give any arbitrary answer. We should have at least some idea of what we are going to say and about what we are going to say. For example, if we say that we want to do research in quantum information, there are two words, quantum and information. So one has to know a little bit about quantum and a little bit about information. Okay, since normally the people who will watch this channel, they will be from physics background. So if one appears in some department of physics anywhere, so the focus is not that much on information aspect. People may ask some question, what is information and how it is measured, quantification, etc. But the major emphasis is on the word quantum. So what they try to sort of assess during your interview is how firm your background knowledge is in quantum information or in quantum mechanics in general. So when we talk about quantum mechanics, so uh, we will roughly the questions which will be asked in interview, the level of those questions is the same as we face in the competitive exam. The only difference is that one should not only memorize the formula, one should know how to, suppose someone asks you to manipulate or some different kind of problem, then one should be able to tackle that thing. So as a very simple example, let us say we have studied particle in a box. Okay, so let us say we have solved that particle in a box problem, and the boundary of the box is from minus L to plus L. Okay, so we have solved for this thing. Now in an interview, people may ask you or the person that the boundary of the box is not from minus L to L, rather it is from 0 to L. Okay, so it is not that one should get stumped out. Okay, so if one knows Schrodinger equation, if one knows how to put the potential profile in that and solve for sign, then one will be able to solve that thing. So that is sort of the meaning, that is an idea through which one can work out.
Yes, sir. So, can you give some examples of questions that you have faced during your interview, or you think these questions could be important and relevant for candidates to prepare if they are giving interview and they have mentioned that quantum mechanics could be one of their subject or studied subject that could be
Yeah.
asked?
So if one says that quantum mechanics is someone's favorite topic, then one cannot escape Schrodinger equation. So roughly all the things revolve around Schrodinger equation. So what one has to know is so the simplest of the problems, particle in a box, particle on a ring. I will also share my screen and show some questions in a little while. But roughly the list is that particle in a box, one should be very much familiar with. Particle on a ring, one should be very much familiar with. And then when we go to, let us say, these are all 1D problems, one dimensional. Then people may ask you, okay, so what about two-dimensional particle in a sort of in two dimensions you have a particle, free particle. Okay, then three-dimensional thing. Okay, so that is the thing. After that, there is another problem which is analytically solvable, and we know the solution in exact form, and that problem is harmonic oscillator problem. So that problem also one should be familiar with, and one should be familiar with the solutions, etc. That yeah, this is the, for example, the ground state of harmonic oscillator is a Gaussian. Okay, that is also the minimum uncertainty state. So all these things one should be able to know. Another very important question which I have faced and some of my friends have faced, that Schrodinger equation is also second degree in time, meaning second degree in space. We have Laplacian sitting, and first degree in time. So del t and del 2 over del x2. And if one recalls that the diffusion equation that we study in statistical mechanics, that also is first degree in time and second degree in space. And we say that Schrodinger equation is sort of a wave equation. Okay, we use the word wave mechanics. Whereas the wave equation that we know of, the Maxwell's equation, that is second order in time and second order in space. So why is it that, meaning this question has been asked, that is Schrodinger equation a wave equation or is Schrodinger equation diffusion equation? This the viewers can also look at, and they may try to solve this thing or give their opinion in comments, and then we can discuss in the next video if possible. So that is one of the questions. So where I was that first thing is particle in a box, then particle on a ring, then this simple harmonic oscillator, and then the fourth thing is for which we know the solution in the closed form, and that is hydrogen atom problem. So these three or four things, these things should be familiar with the student. And the second thing is that spin thing, because most of the quantum information that we do is for finite dimensional systems, meaning for a system with two energy levels, three levels, four levels. So spin plays a very important role. Spin half system, etc. So these are the topics that one should have a little bit of background on. Okay. Now I will share my screen. If you have any other question, then we can discuss that, and then I will share the screen.
I just want to just ask you, what do you mean by the closed solution for hydrogen atom?
Okay. So closed solution means that and the Schrodinger equation is a differential equation. So as we all know that we cannot solve any arbitrary differential equation, because the solution requires some integration kind of a thing. So for Schrodinger, for the hydrogen atom problem, we know that the solutions are Leguier polynomials. Okay. For this simple harmonic oscillator, we know that the solutions are Hermite polynomial. Okay. For particle on a box, we know that sine and pi x over L, those kind of solutions exist. Okay. Similarly for particle on a ring. But suppose let us assume a very fictitious potential, some e to the power minus alpha x. Okay. So for that kind of a potential, the Schrodinger equation is not solvable, meaning we do not know the solution in closed form. So since you have raised this issue, so the students may also think, and this is also one of the questions which is asked in interview. We say that particle in a box is there. We say that harmonic oscillator is there, but we are not in physics. Mathematics is just a tool. Okay, we use it as a tool and we want to gain some insight on physical problem. So is it that some realistic potential is there which is of the harmonic oscillator form? No realistic potential is of the harmonic oscillator form if the full profile of the potential is looked at. Okay, so either one has to solve the for that realistic potential numerically. There, the role of simulation and programming comes into play, and if one simply wants to approximate that potential, so this is the question which is asked. Suppose one is given in the next video, we will discuss this thing. Suppose one is given any arbitrary profile of a potential, then where can we approximate that potential to be a simple harmonic one? So the answer is that near the minima, a potential behaves as if it is a simple harmonic oscillator. So the energy levels which are drawn. So if one has access only to 2 or 3 or 4 energy levels, then it is as if we are dealing with a simple harmonic oscillator potential. Otherwise, we do not have. So in some competitive exams, this question has been asked that they have given some profile and then they have said that, okay, so what are the energy levels up to which we can approximate the potential to be simple harmonic oscillator? So that is one thing. And by closed form, I mean that it is fully solvable mathematically without taking any recourse to some simulation, etc.
Yes, sir. I understand. Okay, please share your other questions.
Okay. So is my screen visible?
I can see.
Okay, so this is, as I have said, that this is the first problem which one should sort of focus on, particle in a box. So there is one-dimensional box of length L. So the box extends from 0 to L or from minus L by 2 to plus L by 2. And this is the profile that the potential energy inside the box is 0 and infinite outside. In the next thing, we will discuss this thing. And then solve the time independent Schrodinger equation for this system. So these are the questions, typical questions which are asked, that solve the Schrodinger equation to find energy levels and then calculate the normalization constant for the wave function. So first one has to find out the wave function and then find the normalization constant. So this is one question which is asked, very simple question. And after that, this is the second sort of potential profile, that is harmonic oscillator. So here V of x is of this form, half kx square. So again, one has to plug in this form of V in the Schrodinger equation and then solve for it. And one has to find out the energy eigenvalues and the eigenfunctions. And then one can find out the position and momentum expectation values for the ground state wave function and convince oneself that it is a minimum energy minimum uncertainty eigenstate. So this is one of the questions which is asked. And then this is the third problem, hydrogen atom. And this is different from the earlier two problems because this is a problem in 3 dimensions. Earlier, both the problems were in 2 dimensions. So this small r is the radial coordinate. This capital R is the radial wave function. And then solve for this equation. This small l is the angular momentum orbital angular momentum quantum number. So solve for this thing and find the energy levels of for the hydrogen atom. So some people might know from Bohr model that the energies go like 1 over n square with a negative sign. So that negative sign is because it is um, attractive and 1 over n square is the typical dependence on the quantum number of this thing. So principal quantum number. So solution of this thing, and then this radial probability density plot. So this question is asked that calculate the radial probability density and then plot it against R. Okay. So these are the three problems which essentially capture all the essential features. And then one can go on and on that finite square well. So earlier we have infinite square well, and now we have finite square well potential. So V of x is minus V naught. So this minus is because it is attractive. And so earlier you see we had here infinite, that infinite square well potential. Here it is just minus of V naught. And then what are, so this is difference between uh, theoretical exam and an interview. That if one is asked this question, then not only one is asked about finite square well, he or she will be asked to relate with the infinite square well potential. So suppose we keep this V naught to be very, very small, so that corresponds to a very or an almost free particle. And then in the next case, we say that this V naught is very, very large. So that corresponds to particle in an infinite square well. And then people are asked, okay, so give us the two limits, see how the things are behaving in a limiting case. So this is one of the questions. So if one has command over these four kind of questions, most of the things will be under control. Now, since quantum information is done for finite dimensional systems, by finite I mean that the number of levels which are accessible are 2 or 3 or 4. So those systems are realized in spin degrees of freedom. That is why we have this two-level system. So this is a favorite system for quantum information people. So people may be asked about Pauli matrices. So this may be asked sigma x, sigma y, sigma z, what are their properties, verify these commutation relations. These are Levi-Civita symbols epsilon I, j, k. So they take value +1 when I, j, k, all three of them are different and all those things. And then if we have a Hamiltonian of a two-level system, so this is also one of the things which I want to emphasize, that so far whatever we have seen all the problems as time independent problems. The Hamiltonian is something in quantum mechanics which drives the dynamics. So Hamiltonian drives the dynamics. Your viewers might know that e to the power minus iota ht, that is the term through which that time evolution takes place. So if we plug in this form of Hamiltonian, then people are asked in interview that uh, how they how a given wave function is evolving in time. So some form of h is given to you, and then e to the power minus iota ht, and then apply that thing and find out the expectation values as a function of time. So these are roughly the kind of questions which one encounters in an interview. And then this is the last thing, that perturbation theory, time dependent and time independent. This I have not written much about, but in the next few things we can discuss this thing as well. So a very simple example is that there is a hydrogen atom, and let us put that hydrogen atom in a magnetic field or an electric field. So then what kind of a shift we are going to observe in its spectrum? So those kind of questions are answered by using perturbation theory. So if one is appearing for an interview of PhD, so one is expected to know perturbation theory, both time dependent and independent. Yes, Athi,
Yeah.
over to you.
So the list, I hope the list is really helpful for the student that you have shared. And I just want to ask you one thing: that what are the books that a student should follow to make the quantum mechanics a strong tool for interview?
So one book that I really like is the book by Jetili, for the simple reason that it has a lot of examples. That is not to say that the student should not solve. All of us have solved problems. You also know this thing. All of us have solved. But the point is that suppose we get stuck or suppose we get some doubt, then if there is a solution available, then one can simply go to that solution and find out, okay, so yeah, this is the thing which is missing, or which this is the step which I was sort of not getting. So that is the thing that one can look at. So Zetili is one book. Now, if someone is a little bit advanced, so one can look at Griffith's part first. So part first covers up to spin thing, and part second is about that perturbation theory, time dependent, time independent, and after that scattering theory starts. So that is roughly there. But Zetili is good enough, and one should try to practice as many problems as possible. And one more thing I want to emphasize, that in interview, the time is not that much that one is asked to solve a problem, let us say some 4-page solution, that kind of a time, because interview is roughly for 15-20 minutes, except in TIFR, etc., where it goes on for 1 hour or so. So the point is that what the professors are interested in knowing is how one approaches a problem. So suppose some problem is given to a student, and the student, because no matter how much we study, for example, you can always give me some problem which I will not be able to solve. So then general advice is that don't give up straightforwardly. You should, meaning the student should say, and the student should not try to beat about the bush, because those are experienced professors. They will be able to know that you don't know. So you should honestly say that, yeah, in the closed form, I do not know the solution, but yeah, I want to approach the problem, and this is, meaning to this extent I know, and these are the steps that I may apply. This is so, don't skip a problem completely. Try to approach that problem, but also try to make it clear that, yeah, you do not know the problem or the solution completely, so you are approaching that problem, so that people do not think that you are trying to impress, or, and don't make any guesses in interview. That in my opinion, that gives a bad impression, that we don't know and we are simply trying to guess, and we are trying to throw some answers.
That's true. And maybe if a wrong guess could lead to like cancellation or bad impact on the
Yes,
professor.
correct, correct.
So as you have suggested in the last video, you have talked about how to like what are the scopes in quantum information theory and how to proceed and what are the suggestions for the student who want to pursue research as their career. Now, many of the students ask me what are the institutes in India or abroad they can go for, especially for quantum information theory, or if you, in a broader sense, like theoretical physics, what are the good institutes they should join?
So in India, there is an exam called JEST. So the students may look at the poster of JEST, and there are some, I think, close to 20-25 institutes which take part in that exam, and the admission is done based on the score in that particular exam. So what I am trying to say is that mm, uh, the kind of best institutes are, for example, TIFR is there. In TIFR, theoretical quantum information is not done. Okay, some superconducting quantum information, and they are trying to build a quantum computer. If I remember the name correctly, Vijay Raghavan is there. So then there is an institute, HRI, Allahabad, now Prayagraj. So that HRI thing is there. RRI is there, Raman Research Institute, Bangalore. IISC is there. In IISC, again, theoretical quantum information is not done. They are interested in the experimental aspects. So, and that is there. RRI also, photonic quantum information is there. And after that, PRL Ahmedabad, that is a center for experimental quantum key distribution. Theoretical quantum information, mostly, I'm not saying fully, but mostly it is done in Kolkata. So there are institutes like SN Bose. Uh, I think it is called SN Bose Center for Basic Sciences, or that is the full name. So there are two professors there, Manik Banik and Arjun Majumdar. And then after that, there is Bose Institute there. Then after that, there is ISI Kolkata, which is there. So in all these places, theoretical quantum information is pursued. Then after that, IISER Kolkata is there. That is also a good center of theoretical quantum information. Then there is TCZ Crest. So that is a new center which has opened recently, I think some 2, 3 years back. So so two professors I know who are there. One is Professor Pankaj Agrawal, another is Professor Arun Kumar Pati. So Professor Pati has recently shifted there. So that is a good center for theoretical quantum information. Then after that, there is a center in Hyderabad, not one center, but two centers. One is Triple IT Hyderabad. I do not remember the full name, but yeah, that is there. So some professors are there. And then one more place in Hyderabad. I'm sorry, I'm skipping the name because I don't know. So that is there. Then after that, IITs, they are there. So in IITs, IIT Bombay has a strong quantum information group. IISER Mohali has a group. In IIT Delhi, people work on photonic quantum information. As far as I know, there are three professors. Professor Bhaskar Kanseri, photonic quantum information. Professor Joy Ghosh, again photonic quantum information. And Professor Bodhaditya Santra, he works on cold atoms. So that is the thing. And IIT Kanpur has some people, for example, Professor A.K. Jha is there. And after that, IIT Bombay has recruited recently many people. So if you want me to take names, so Professor Himadri Shekhar is there. Professor Soumya Bera is there. Professor Professor Sai was there. Recently, if I remember correctly, he has shifted to London. So that is the roughly the landscape. Let me recall if I'm missing something. So yeah, one thing. In IIT Madras, recently one center has come. They have opened a center. So that is very, very vibrant center. So recently some 2 or 3 PRL have come from that center. So as I was telling you that from Kolkata also many PRLs have come. So in theoretical quantum information, in from IIT Madras also. So in IIT Madras, Professor Arul Lakshmi Narayan is there, Professor Prabha Mandyam is there, Professor Vaibhav Madhok is there, and then there is Anil Prabhakar is there. Anil Prabhakar is primarily associated to Department of Electrical Engineering in IIT Madras. So these are the places. Now I think I have taken almost all the names. So some things might be skipping, but yeah, this is more or less the situation. Now the second part of your question was, sorry for this long an answer, but the second part of your question was that what about abroad? So in abroad, people are working on quantum information everywhere, So in Asia, in Singapore, people are working like CQT is there, Center for Quantum Technologies. Uh, in China, people are also working. And in Europe, there are many places like Max Planck Institutes are there. In Germany, there is a very good work which is going on. If you want me, I can write some names and then we can write that thing in comment box. So there are many professors which are working there. In Japan also people are working in quantum information, and of course US. So in Cornell there is a professor. So yeah, there is a lot of scope both in India and in abroad. But if one wants to do theoretical quantum information, then primarily one can try either in Allahabad or in Calcutta, because there one will get a lot of exposure.
Okay. Thank you so much. So, students, please note down the professor name and please Google about their profile. If you are interested, you can approach them. And if you are hesitating how to approach, just simply write a mail regarding your interest. And if they have some scope to include you as an intern, definitely they will reply back. So that could be a possible way for starting. Otherwise, you can directly qualify JEST or GATE or NetJRF, and then you will go to interviews and you will crack the interview and get position, admission for PhD, and approach the professor for pursuing your study. So thank you all thank you, sir, for giving time and your really I appreciate your time and one by one discuss step by step discussion for uh, all these topics, which is very important for all the students, and giving us the time from your busy schedule and all for the students. And thank you so much. I once again I appreciate. And okay, students, we are we are going to end this lecture, and I hope this video is helpful for you. So please like the channel and please share the video with all the ready students and please subscribe the channel. Thank you so much for watching this video.